Assalamu alaikum everyone. Welcome to a brand new video of Chess Academy. In this paper, I will be solving in detail a physics past paper of October-November 2023, variant 2 paper. So let's waste no more time and let's get started. The total mark to this paper is 80 and we need to answer all of the questions. So in question 1a, it asks for velocity is a vector quantity but speed is a scalar quantity. A. State how a vector quantity differs from a scalar quantity. It's a very easy difference. We all know that vector quantity has a direction and scalar quantity doesn't. So let's write vector vector quantity has has a direction and scalar quantity does not. Sorry. Quantity does. So done. We got the one-on-one for question 1A. So in question 1B, underline all the vector quantities in the list. So let's see which of these quantities shown are vector quantities. We know that acceleration is a vector quantity, so let's underline acceleration. Distance is not a vector quantity. Displacement is a vector quantity. Distance is a scalar quantity, so not distance. Energy is also not a vector quantity. Energy, mass, energy and mass both are not vector quantities, both are scalar quantities. Thus, we cannot underline below energy and mass. Momentum is a vector quantity. So let's underline below momentum. Temperature is a scalar quantity. Temperature does not have any particular direction. Momentum and acceleration are the only two quantities amongst these six quantities that have a particular direction along with the magnitude. All the other one, two, three, four. All the other four quantities have only magnitude but not direction. Only acceleration and momentum have a magnitude along with direction. So let's go on with part C. In part C, it says that figure 1.1 shows a passenger running across a large ship at right angles. Okay, so there is the passenger and it's running at right angles across a large ship to the direction in which the ship is moving. Okay, the ship is moving due east and the passenger is running due north at a 90-degree angle. The passenger runs across the ship at 2.4 meters due north, 2.4 meter per second due north. A large ship is traveling due east at 6.8 meters per second. Determine either graphically or by calculation the resultant velocity of the passenger. Give the direction in which the passenger is moving relative to due north. Give the direction in which the passenger is moving relative to due north. Show your answer. Show how the answer is obtained. So let's draw a diagram in which I mark this as north and this as east. So the question says the man is running at a speed of 2.4 meters per second due north and a speed of 6.8 meters per second due south. So it asks for the resultant velocity. So we know that to find the resultant velocity of two perpendicular components, we use the Pythagorean theorem. That is, we find the length of the hypotenuse. Sorry, my drawing is not that good because I am poor in drawing straight lines. So we find the length of the hypotenuse. So we find the length of x. So what do? According to the Pythagorean theorem, if this is a, if this is b, and this is x, then the formula would become a square plus b square is equals to x square. So let's do it. 2.4 square plus 6.8 square is equals x square. So now let's make x subject to find the resultant velocity. Okay. So what is 3.4 square plus 6.8 square? 0.4 square plus 6. It's a 52. So x square becomes 52, and then x would be root 52, that is 7.2. Yes, one more thing, we always have to put our answer to the same number of significant figures as given in the question. Like in the question, the num values, the 2.4 and 6.8 are both given to two significant figures. Thus, we must also give our answer to two significant figures. So, the a value, the velocity becomes 7.2 m s inverse. So, we have one more part to this question, that is, it asks for the direction in which the passenger is moving relative to due north. So, we know the magnitude is 7.2 meters per second. So, let's write the magnitude first, 7.2 meters per second. And now we need to find the angle. Like if this is the north, this is north, and this is the resultant velocity v, we need to find this angle, theta. Let's now call it theta. At dash degree from due north. So as this is north, this is velocity, the resultant velocity, we need to find this angle. So how do we find it? We know that if this speed, if the vertical, well, the speed towards the north is 2.4, and the speed towards the south, not south actually, east, is 6.8, then we can find the theta by using the formula tan theta is equals to 6.8. Opposite by adjacent. Here the opposite is 6.8 and the adjacent is 2.4. So now let's make theta subject to get the angle. Tan theta 6.8 by 6.8 divided by 2.4 becomes 6.8 by 2.4 becomes 17 by 6. Now let's just use the calculator to find the angle. So the angle becomes 70.6. Or we always put angles at one decimal place. Thus 70.6. Let's match our answers to the mark scheme. In the mark scheme, the answer, the speed is between 7.1 to 7.3. Our speed was 7.2, thus now within the marks, within the range. And the angle was between 18 to 21 degrees. So let's see, did we get it? Yes, so yes, the angle was between 69 to 72 degrees. So our answer was 70.6 degrees. Thus, our answer lies between the range of mark scheme. Thus, we got a full mark. That is 6 on 6, 4 on 4 on this part, and the 6 on 6 on the entire question. Now, let's move on to question 2. In question 2, it says that a speed craft of mass 300 kg is moving in a straight line in space at a speed of 8,000 meters per second. Calculate the momentum of the spacecraft. A very easy question. We know the formula of momentum is P. P is the symbol of momentum. P is equals to mv. So we just multiply the mass and the velocity. 300 mass multiply velocity 8,000. So we get 300 multiplied by 8,000. 24. 2.4 into 10 to the power 6. This is our answer. It was a very easy question. Now let's look on to part B. In part B, it says that the fuel on the spacecraft explodes and the spacecraft splits into two parts. The direction in which the parts move does not change. Okay. After the explosion, the speed of the front part increases to 9,000 meters per second. It has a mass of 150 kg. Calculate the speed of the rear part after the explosion. Okay. So it says that there was a spacecraft. It exploded into two parts. Like this, there's a spacecraft. It exploded into two parts. This is again. This is 9,000 meters per second. One part. This is 9,000 meters per second, and this part went with a speed of v that we don't know. We have to find. So, so we know that this. It's also said that said that the question also says that the direction the direction in which the parts move does not change, which means after explosion, as the let's assume the spacecraft was moving towards the right at a speed of 8,000 meters per second. We The question previously told that the spacecraft was moving at a speed of 8,000 meters per second. Now we are just assuming it's moving towards the right. Okay. So as the directions doesn't change, so after explosion, the parts should also move towards the right. So this velocity, this v, is actually towards the right. This velocity is actually towards the right. Now we are told to find the velocity, this value of v. So we know according to the law of conservation of momentum, the initial momentum must be equal to the final momentum. So what was the initial momentum? The initial momentum was 2.4 into 10 to the power 6. This was the initial momentum. Thus, this should be equal to the final momentum. What is the final momentum? The summation of the momentum of individual parts. Like there were two parts. There were two parts, and we need to add the momentum of both the parts. Like so, the momentum of one part that we know it has a mass of after explosion speed in the front. Okay, the mass of the front part is 150 kg, and it has a speed of 9,000. So let's multiply it with 9,000. Now we need to add the momentum of the rear part. So if the total mass of the spacecraft was 300 kg and the mass of the front part is 150 kg, then what should be the mass of the rear part? It should be 300 minus 150. That is actually 150. So the front part weighs 150 kg. The rear part also weighs 150 kg. So let's multiply 150, and the speed of the rear part is v. So here we just have to make v subject to get this the velocity of the rear part. Let's do it. So what do we do? 2.4 multiplied by 10 to the power 6 is equals to 150 times 9,000. It becomes 1.35 into 10 to the power 6 plus 150v. So 150v becomes 2.4 into 10 to the power 6 minus 1.35 into 10 to the power 6. If I take 1.35 into 10 to the power minus 6 to the other side, it gets subtracted from 2.4 into 10 to the power minus 6, then it becomes 1.05 into 10 to the power minus 6, 10 to the power 6, not minus 6, into 10 to the power 6. Now if we bring 150 to the other side, it gets divided with then we divide. If we take 150 to the other side, a division sign comes in, so it becomes 1.05 into 10 to the power 6 by 150. Now the value of v becomes 7,000. Let's check it. In the mass scheme, yes, mass scheme, the initial momentum was 2.4 into 10 to the power minus 6, thus we got it right, and the final momentum was also 10,000. 7,000. So we got both of the questions right. So we got a 3 on 3. Now let's move on to the part 2. The total kinetic energy of the two parts after explosion is greater than the original kinetic energy of the space. State the energy transfer that occurred in the explosion. Okay. So we see that we know that the energy cannot be destroyed, neither produced. Thus, here the kinetic energy has increased. Total kinetic energy has increased. Thus, previously there was a different form of energy that got converted to the additional kinetic energy. Thus, let's see what kind of energy might be there previously. As the question says, the fuel on the spacecraft explodes. So we know that the fuel has chemical energy. It explodes to cause an increase in kinetic energy. Thus, we can say that initially there was chemical energy. There was, let's not write initially, then the answer would be too long. Let's just write chemical energy got converted to kinetic energy. Got converted to kinetic energy. This is the only answer to this question. Let's look at the mark scheme. Yes, in the mark scheme, from energy stored as chemical potential energy. Okay, so we in the mark scheme states that chemical energy was converted from. By saying from, they mean that chemical energy was converted to K. So our answer technically means the same thing. Also, one more thing, we do not have to write the exact thing from the mark scheme. We just need to keep the idea same. Like here, whatever I wrote as the answer is not exactly as what is written on the mark scheme, but the idea is the same. As the idea is the same, we will get the marks. So the marks I get is 1 on 1. Now let's move on to part 3. In part 3, it says that the explosion lasts for 0.2 seconds. Calculate the average force on the front part during this time. Okay. So we know the formula of force according to Newton's second law is force is equals to del P, which is change in momentum by change in time. So the change in time here is 0.2 seconds. So what's the change in momentum? Let's see. Force is equals to one more thing. Instead of just writing del P, I can also write mv, mass into vf minus vi. By vf I mean velocity final minus velocity initial by delta t. So we know, let's find out the force. We know the mass of the front. Yes, we are told to find the average force on the front part, not the rear part. So let's see what's the mass of the front part. The mass of the front part is 150 kg. So first let's fill up the equation by filling up the value of mass. Then what is the velocity final? The final velocity is 9,000 and the initial velocity was 8,000. As the initial velocity of the entire spacecraft initially was 8,000, thus the velocity of the front part initially should also be 8,000, as the spacecraft and the front part was the same initially. Thus, the initial velocity is 8,000 and the final velocity is 9,000. 9,000 minus 8,000 by time. What is the del T? 0.2. Now we just need to put these values into the calculator to get the answer. 9,000 minus 8,000 multiplied by 150 by 0.2. So the average force becomes 7.5 into 10 to the power 5. So this is, yes, in this question we are given with a 2SF value for the time. Thus, we put a 2 significant bigger value for the force as well. So the answer becomes 7.5 Newton to the power 5 newtons. Let's look at the mark scheme. Was the answer? Yes, in the mark scheme, we are also given with 7.5 into 10 to the power 5 newtons. So thus, we are correct. So we got a 9 out of 9 in part 2. Now let's move on to part 3, question 3. So question 3 says that a plain irregular lamina has a mass of 50 gram. It hangs from a nail that passes through a small hole H. This is H, near to the edge of the lamina. Okay, this is the edge, this is the edge, and this is edge. The nail acts as a pivot and the lamina can swing about it. The lamina is held in the position shown in figure 3.1, a small distance above a horizontal bench. Where is the horizontal bench? Okay, here it is. So a small distance above the horizontal bench, the lamina is held at this position. Okay, now let's see. What's next? The center of gravity of the lamina is at G. So at G, this is the center of gravity and this is the pivot at H. The weight of the lamina is a force that acts downwards. Explain why the lamina experiences this downward force. Very easy. Why do any object experiences force? Because it has mass and it's in the Earth's magnetic field. So the answer is it has mass and it is in the Earth's. Earth's. We have to write Earth's because weight is caused due to the Earth's magnetic field. Earth's not magnetic, gravitational field. Let's look what's in the mark scheme. So in 3A1, the mark scheme says it is in the gravitational field of the Earth. So we wrote the same thing actually. Our answer did not match what's on the mark scheme word by word, but the idea is the same. Thus, our answer is correct. Now let's move on by part 2 of part A. Calculate the weight of the lamina on the Earth. Very easy. The formula of weight is mg, that is equals to mass into g, which is the gravitational according to Newton's second law. So what is the mass? The mass is 50 grams. So we need to convert this into the SI unit of mass. Thus, to convert 50 grams to kg, we need to divide 50 by 1000 into g. What is g? 9.8. In the beginning of the question paper, on the front page, it was written that to use 9.8 as the value of g. Thus, I'm using 9.8, but not 10. So if we put these values into the calculator, we get 0.49. So the weight is 0.49. Sorry, 5, it's 49. Let's look at the mark scheme. Yes, in the mark scheme, the weight is 0.49. So we got the mass. So let's move on to part B. In part B, it asks that the weight produces a moment about the pivot through H. Okay. Using figure 3.1, calculate the moment of the weight about the pivot. Okay. So we know that the formula of moment is force, that is the weight, into perpendicular distance. What is the perpendicular distance of the center of mass? Yes, we know that the weight acts towards the through the center of mass vertically downwards. So the weight is acting through G vertically downwards. This is W. And what is the perpendicular distance of the center of mass to the pivot? It is 8. If this is the line of axis like this, if this is the line of axis of the weight, and this is the pivot, then the perpendicular distance is 8 centimeter as given. This is the perpendicular line. Let's use a different color, red. This is the perpendicular distance. The line marked with red, shaded with red. So the perpendicular distance is 8 centimeter. Now let's do the calculations. The weight is 0.49 and the perpendicular distance is 8 centimeter. We need to convert 8 centimeter into meter as meter is the SI unit. So moment, that is M, is equals to, what is weight? 0.49 multiplied by moment, that perpendicular distance was 8 centimeter, 8 by 100. To convert 8 centimeter to millimeter, we divide it with 100. So 0.49 into 8 by 100. It becomes 0.039. So this is the answer. Now let's move on to part 2. The part 2 is a descriptive question. So before solving this question, one thing you should know, always after solving such questions that are descriptive, you should always look at the mark scheme, because you might give a description which might not, which might be right, but yet not match the mark scheme. Thus, you should always, after answering the descriptive question, you should look what's written in the mark scheme and try to match your answer. So our aim is to write. Our aim is to give an answer that is as close as possible to the mark scheme. Now let's see what the question says. The lamina is now released from the position shown in figure 3.1. Describe what happens to the lamina from the time it is released until it stops moving. Okay. So as we know, the lamina experiences a moment due to the weight, and as we are holding the lamina, thus we are providing an reverse moment that's cancelling the moment due to the weight, causing zero moment. Now, as we release the lamina, it will experience this moment, 0.039 Newton meter, which would cause the lamina to move in which direction? In clockwise direction, as the weight is causing a clockwise motion. So the oscillation of the lamina would be in the clockwise direction initially. So let's first write initially. For there 3 marks, so we need to write 3 informations. So the first information is it. By saying it, I mean lamina. It initially rotates in the clockwise direction. This direction. Now, what happens after it starts rotating in the clockwise direction? It will initially gain speed when it is rotating in the clockwise direction. As it initially gains speed, then afterward, what happens? It loses speed when the center of mass starts to give upwards. Like when it's swinging in the clockwise direction, the center of mass is getting downwards, which would cause a decrease in GP and increase in KE. Thus, speed increases. So in this segment, V increases, and in this segment, V decreases. Because the center of mass at this segment is rising, which would cause an increase in GP and decrease in K. The K is being converted to GP. That's the basic thing. So we would write it oscillates. Simply we can write it oscillates. Oscillates, it would mean that it is initially gaining speed, then losing speed, then it's getting back to its original position. By saying original position, I mean like the lamina first goes this way, then it goes back to this way, then back this way, and again back this way. So this is called oscillation. So it will keep on oscillating, and at one point it will come to a stop with the center of mass vertically below the pivot, so that the perpendicular distance between the center of mass and the pivot becomes zero. So no moment, thus no rotation. The moment is causing the rotation. So if the perpendicular moment is zero, the rotation will also be zero. Thus the lamina comes to a stop with the center of mass vertically below the pivot. So let's write the second point. The second point is it oscillates. Oscillates. That's it. It oscillates, which means it goes first this way, then that way, then again this way, then again that. This is what oscillation means. Okay. Then the third point is then it comes to a stop. Sorry, not it's. It comes to a stop with its center of mass. Yes, center of mass was indicated by G. Like here, the center of mass was indicated by G. Thus, we can write G instead of center of mass because G means center of mass. With G vertically below, because yes, we know that the weight is weight acts vertically. So if G is vertically below the pivot, then the perpendicular distance between the weight and between the center of mass and the pivot becomes zero. So zero moment. So with G vertically below the pivot. So let's see what's written in the mark scheme. If we are were we able to answer everything according to the mark scheme? Let's check. So in the mark scheme says the lamina moves clockwise. Yes, we did write clockwise. Yes. About the pivot, we didn't write about the pivot, but as about the pivot is between brackets, thus it is not important. Even if we don't write whatever it is written in the brackets, we will still get this mark. This is an exception. The brackets are just stuff that are not required, but if you write it, it is good. So in this, we got the first mark. In the second mark, what does it say? For the second mark, we needed to write it oscillates. Yes, it speeds up and then slows down, or it oscillates. So we did write it oscillates. Thus, we got the second mark as well with decreasing amplitude. We don't need to, as this is also in brackets. Thus, we do not need to write decreasing amplitude or overshoots. So we wrote it oscillates. We got that. For the third mark, we need to write it stops G vertically below H. So we did H. Yes, H is the pivot. The pivot was indicated by H. Thus, instead of pivot, they wrote H. So G vertically below pivot. It stops with G vertically below pivot. So did we write that? Yes. It comes to a stop with G vertically below the pivot. So we were successful in gaining 3 marks out of 3 in this question. So let's move on to the next question. That is part question. So question 4 says that figure 4.1 shows a long vertical tube sealed at the base and open at the other end. Tube is 1 meter long. So let's look at the tube. This is the open end and this is the base, sealed base. Okay. The tube is 1 meter long. The cross section area of the tube is 4.0 into 10 to the minus 4. So the base of the cross section area is 4 into 10 to the minus 4 meters. It is filled with a liquid of density 1.4 into 10 to the 4 kg per meter cube, the density of the fluid liquid inside the tube. And we are told the atmospheric pressure is 1 into 10 to the 5 pascals. Calculate the total pressure in the liquid at the bottom of the tube. So we know at the bottom of the tube, at the top of the tube, the surface of the liquid experiences the atmospheric pressure, which means at this point, the pressure is 1.0 into 10 to the power 5 pascals. At the top of the liquid surface, the pressure is 1.0 into 10 to the 5 pascals. And what's the pressure at the base of the tube? It is the pressure due to the liquid plus the atmospheric pressure, because at the base we experience both the atmospheric pressure and the pressure due to the liquid. As that, there's no as. Now let's move on. The total pressure in the liquid at the bottom of the tube. So let's calculate. So the formula of pressure is P is equals to H rho G. Here H is the height, rho is density, and G is gravitational acceleration. So rho, what is rho? What is the density of the liquid? It is 1.4 into 10 to the power 4. Okay. Let's put the values. 1.4 into 10 to the power 4 multiplied by height. The height is 1 meter. The height of the liquid is 1 meter. As the height of the tube is 1 meter and the entire tube is filled with the liquid. Thus, the height of the liquid is 1 meter multiplied by G divided by. And we add along, this is the pressure due to the water, H rho G. Sorry, not the water. This is the pressure due to the liquid, not water, liquid. So with this pressure, we need to add atmospheric pressure, that is called ATM. By saying ATM, I mean atmospheric pressure. So what is the atmospheric pressure? 1.0 into 10 to the power 5. So we need to add this much to this. This is the liquid pressure and this is the atmospheric pressure. We add these two to get the floor pressure at the base. Let's put the values into the calculator to find the answer to this question. So we get one thing, the values in the question, the given values in the question has a two significant figure value. Like this value has two significant, this value is 2 SM, two significant figures. Thus, our answer should also be of two significant figures. So the answer is 2.4, sorry, 2.4 into 10 to the power 5. Let's look at the mark scheme. Yes, the mark scheme also says the answer to be 2.4 into 10 to the power 5 pascals. So we got the answer. Let's move on to part 2. The force exerted on the inside surface of the bottom of the tube. Okay, so we know that the formula of pressure is also E is equals to force divided by area. So if you make F subject, F is equals to PA, with the pressure multiplied by area. So the force becomes pressure. What is the pressure? 2.4 into 10 to the power 5 multiplied by what was the base area? The base area was 4 into 10 to the power minus 12. Let's put this value 4 into 10 to the power minus 12. So we, after putting these values into the calculator, we get 96. The force is 96 newtons. Let's look at the mark scheme. Yes, it's a 96 meter or 90. We got 96, so we got the mark. So we got a full marks in part A. Now let's go on to part B. So part B says that a small sheet of glass placed over the open end of the tube. The tube is inverted in a container of dense liquid. The open end of the tube and the sheet of the glass are a short distance below the surface of the ground. Figure 4.2 shows the arrangement. Here we can see that the tube has been inverted. Previously, the open end was at the top and the sealed end was at the bottom. Now the open end is at the bottom and the sealed end is at the top. Thus, the tube has been inverted and we can see the sheet of glass. So, what does the question asks? Let's see. The question says the sheet of the glass seals the open end of the inverted tube. Describe what happens in the inverted tube when the sheet of the glass is removed. What happens? So let's see. If we remove the sheet of this glass, what would happen? Simple. The liquid inside the tube would start to fall out. It will start to fall out and create a vacuum on top. Like if I say, oh, sorry. It will create a vacuum on top, and at the end, the liquid level would stabilize at a point, particular height. Like let me say for example, the liquid height where it stabilized is here, and we would say this much distance as the height of the liquid inside the tube, and over here you would see a vacuum. The entire part of the tube that is above the liquid surface would be a vacuum, and there is no air to fill this much space. Sorry. Vacuum. And one more thing is, why did this liquid even stabilize? You could have said that the liquid completely fall out from the tube and go to the container. Why did it chose to stabilize at a particular height? This is because of atmospheric pressure. The atmospheric pressure is acting at this. Sorry, this is this. These are ATM pressure. The ATM pressure is acting downwards at the surface of the liquid, which is also pushing the liquid inside the tube. But there is no pressure due to this vacuum at the top of the tube. So due to this atmospheric pressure, we can see a height of the liquid. This much height of the liquid would The pressure due to this much height of the liquid would be equal to the atmospheric pressure, because the atmospheric pressure is causing this much, causing the liquid to stabilize at this height. So as we are asked to describe what happens, let's say the tube, the liquid from the tube, the tube falls out, falls out. Then we say, sorry, let's not give the full stop, creating a OUT, creating a vacuum on top. A vacuum, vacuum on top of the tube. Or tube plus tube. I wrote D instead of B. Sorry. Tube. Now the full stop. Sorry. After that, we have two more lines and two more marks to gain. If this much information got us 1 mark, what else do we need to write to gain the rest 2 marks? So we can write that the height of the liquid, the pressure due to the height of the liquid, the stabilizes at a particular height above the surface of the water at the container. So let's write it. The liquid stops at a particular height the height above the surface of the liquid in the container. So one more thing we can write is that the pressure due to the liquid is equal to the atmospheric pressure. The pressure due to the liquid in the pressure due to that much height of the liquid is equal to the atmospheric pressure. Like the pressure due to the liquid of this height of H height is equal to the atmospheric pressure. That's what we need to write. So let's write it. The pressure here versus pressure due to the liquid in the, instead of writing height, we can write the pressure due to the liquid in the tube equals the atmospheric pressure, ATM pressure. In your exam, you cannot write ATM, you have to write atmospheric. I wrote the short form just to save time. So you might notice that I wrote below the given space. That won't be a problem actually. In your exam, you can also choose to write below the given space for a maximum of 2 lines. Like, say for example, here 1, 2, 3, 4, 5. 5 lines were given. I wrote about 6 minutes. You can choose to write about 7 lines when there are 5 lines given, but try not to exceed the given space. If you don't have enough space, you may choose to write below the line. So let's see how many marks did we gain from this answer. The mark scheme says that the liquid falls. Yes, we wrote this part, so we got 1 on 1 from this part. It then stops falling, which means reaches stability. We did write this part as well. It stops at a particular height. So we got this mark as well. Now in the third mark, it says pressure of the liquid at the bottom tube greater than the pressure of the liquid in the basin immediately beneath it. We didn't write this thing, but we did write the or part. Like it said, you can write any of these 3 things as there is an or mention. So we can write any of these three lines. So did we write the second line? Pressure becomes equal to the atmospheric pressure. Yes, we did write this. Then we also wrote leaving a vacuum. So we did also write this one. So technically we should get 4 marks, but we would eventually get 3 marks because these the examiners will check out one of these two. They won't consider two of these, they would consider one of these two. So if you write both of them, they will just look at the first one. Like if I write creating a vacuum, as I wrote creating a vacuum in the first line, thus they will look at creating a vacuum and give you that mark. So eventually we got three right, one, two, and three, and they didn't come this one because as we got the full marks available. Now let's move on to question part 2. This equipment is used to make a measurement that is used to calculate atmospheric pressure. Describe the measurement made and then used in the calculation of atmospheric pressure. You may draw a diagram to it. Okay. First, let's draw a diagram to explain you. Let's say this is the container. This is the level of the liquid in the container. This is the tube. This is the level of the liquid inside the tube. We won't see a line here. Okay. So this is the level of the liquid inside the tube, and this height is h. Then, as I said in the previous question, as in the answer, I said that the pressure due to this much height of liquid is equals the atmospheric pressure. So to find the atmospheric pressure, the question says describe the measurement made and then used to calculate in the calculation of atmospheric pressure. You may draw a diagram in your home. So I drew a diagram and marked this height as h slash meter. By saying slash, I mean the unit of h is meter. Now I just simply write measure h, and then use the formula of pressure is equals to h rho g to find the atmospheric pressure, ATM pressure. Here rho means density of liquid. Let's see how many marks did we get in this part. Height of the liquid surface in the tube measured. Yes, by saying height of the liquid on the tube surface, we mean this height. So I did mention measure h. By saying measure h, we mean height of the liquid surface. So this is the same thing in the tube. Yes, height of the liquid surface in the tube. So we got this part right. So in the second part, for the second mark, it's told that measure relative to the level of the liquid surface in the container, or h rho g used to calculate the pressure. Yes. So we did mention h rho g used to calculate the pressure. So we got this mark as well. So we got a 2 on 2 on this part. Now let's move on to question number 5. So question 5 says that figure 5.1 shows a device that cools the air in a room by evaporation. The figure shows there's some water in a container, wet sponge block, 2 grills, and a fan. Okay, next. Water drips from the container into the sponge block and it keeps it wet. Air flows in through one grill and out through other. As the air flows through the wet sponge block, the water in the sponge block evaporates. Okay. A. When the water evaporates, the temperature of the water remaining in the sponge block decreases. Explain in terms of movement of particles why this decrease in temperature. This is a very simple question and it has a very simple answer because the question asks why evaporation causes cooling. So let's find out why it causes cooling. Evaporation causes cooling. Let's assume we have a bowl of water. So always when evaporation occurs, high energy particles or water molecules at the surface of the water, that is here, at the surface of the water escapes the water body. high energy molecules at the surface of the water escapes. This curved, not curved, this exact line represents high energy molecule. High energy particles. Molecules, particles basically means the same thing in this, for this case, not in every case, but this case. Okay, so high energy particles escapes the liquid surface, or thus the remaining particles that's in the water have a lower energy than those high energy particles. Thus, the total average energy of the remaining water body is lower than it was before. Because previously there were a few high energy particles with the low energy particles, but now the high energy particles escape left. So we just have the low energy particles, causing the average energy, which is actually the kinetic energy of the particles, to decrease. Temperature temperature of liquid actually means the kinetic and average kinetic energy of the particles. So the average kinetic energy of the particles decreases. So let's see how we should write the answer. So we should explain in terms of movements of particles. Thus, we should include this part in our answer. So let's start. The mark is 2, so thus we should write 2 points. So for the first point, then I write uh, high energy or fast moving particles. High energy fast moving particles basically means the same thing. High energy particles escape from the water. This is one point. And the next point is, thus the remaining energy, remaining particles have less average kinetic energy. So this is all we should write to get the 2 marks. Let's look at the mark scheme. The mark scheme says faster in 5A1, faster moving particles, which has actually high energy particles, are more likely to escape. We don't need to write the more likely because it's in the brackets. The whatever is in the brackets is not mandatory that you should write. Okay. So as there is a dashed line below the particle, thus we should write particles. The particles is the key. The word particles is the key point of this mark to achieve this mark. Thus, as we wrote, high energy particles, which is actually fast moving particles, escape. Thus, we got the first mark. Let's look at the second mark. For the second mark, we had to write remaining particles have less average kinetic energy. So we wrote this. Remaining particles have less average kinetic energy. So as we wrote this, we got the second mark as well. So we got 2 on 2 in this segment. So let's go on to the next part 2. Explain why energy is needed when water evaporates. It's a very simple, and it also has a very simple explanation and an answer. As the water molecules are escaping, we must provide a little bit of energy to cause the high energy particles to escape, overcoming the attraction force between the water molecules. There is an attraction force between the particles, so we must give some energy to overcome those attraction force. So let's write an answer. Energy must be supplied to move particles against the attraction forces. The attraction forces. Let's look at the mark scheme. The mark scheme says work is done, which is energy is used, moving particles apart against forces of attraction. So we wrote this part, moving particles against the forces of attraction. So we got this mark as well. Now let's look at the part B. Say two ways in which evaporation differs from water. So it asks two differences between evaporation and water. So as it asks two ways which state two ways in which evaporation differs from boiling. Thus, we should write properties of evaporation instead of boiling. Thus, let's look at the first point. We know that evaporation occurs at the surface. So let's write evaporation occurs CCURS occurs at the surface. That's one difference. And the next difference could be during, yes, whenever boiling occurs, we experience some bubbling in the water. We do see some bubbling, but we never see bubbling during evaporation. Like evaporation occurs every time, at every liquid state, with every liquid at any state, not at any temperature. At liquid state, at any temperature, evaporation occurs. Like water, if you have a glass of water and the water is at a temperature of 10 degrees Celsius, yet evaporation occurs because evaporation occurs at every temperature within the melting and boiling point of the liquid at its liquid state actually. At its liquid state, evaporation occurs at all temperature. Thus, we never see as thus we always thus evaporation occurs at every times, but we never see the bubbling in evaporation. Thus, we can say no bubbling in evaporation, but we can see bubbling in boiling. Thus, no bubbling in evaporation is a difference between evaporation and boiling. Let's look at the mark scheme. The mark scheme says any two from, let's see, we just need to write any two of these three. So let's see, did we write the two? No bubbles formed. Yes, we wrote this part. We got one mark. Occurs at any temperature. We didn't write this, but we did write the third one. That is, oh no, I think we missed one point. It says no bubbles formed or occurs at the surface, but which means we can't write these two as two different sets. We need to write either of these two. If you write both, we just get one mark. But if you write both of them, if you write one of them, you'll still get a one mark. Thus, we cannot write both of them. We wrote no bubbles formed and occurs at the surface. Thus, we will just be getting one mark because there is an or between these two. So any two from these three, but not these two. So we'll just be getting one mark. So to get the other one, what could we write? That is occurs at any temperature. We know that evaporation occurs at any temperature. We could have written that. We also could have written that it is affected by exposed area, that is the surface area. We know that the evaporation occurs at surface. Thus, more the surface area, more the evaporation. Lower the surface area, lower the evaporation. Thus, but in case of boiling, the surface area does not matter. And in case of boiling, the boiling occurs at a fixed temperature, not at any temperature. Evaporation occurs at any temperature. Thus, we could have written these two, but we missed out. Thus, we will just be getting one out of this thing. So in your exams, you should be careful of these tips. Now let's move on to question 6. So question 6 says that the loudspeaker shown in figure 6.1 produces a sound of frequency 800 Hz. HZ refers to Hz, which is the unit of frequency. The figure shows a power supply, a loudspeaker, cone of the loudspeaker, and the sound waves getting out of going to the right. Okay. So in part A, the question is state what is meant by frequency. Frequency is the number of wavelength passing a point per unit time. That's the basic definition of frequency, nothing to understand. It's just the basic definition. So we write the book definition from the book, that is the number of wavelengths those wavelengths passing a point per unit time. So this is the definition, and this is the definition from the book. So I guarantee you, by writing this definition, you will be getting full marks. That is 2 on 2. The first mark, there is 2 marks. So the first mark is for the number of wavelengths, and the second mark is for per unit time. Let's look at the mark scheme. Yes, in mark scheme, the 6A says the number of wavelengths, 1 mark, per unit time, 2 marks, second mark. So we got 2 on 2. So in part B says that explain whether the sound produced by the speaker is audible to a human with healthy hearing. Okay. So we know a human with healthy hearing system or procedure, a human who can hear properly, can hear frequencies of between 20 hertz to 20,000 hertz. That is 20 kilohertz, in other words. So a healthy human can hear within this range. So we can say that 800 hertz lies within this range. Thus, we can say yes, 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 the sound can be heard because explain, it says explain. So we need to explain why. Yes, the sound so the sound can be heard because 800 hertz is within the audible range. Audible range means the range of frequency within which human can hear sound. Audible range. Let's look at the mark scheme. Mark scheme says yes and within audible range. Thus, we got the mark because we wrote this. Yes and within audible range. Audible range mean what is the audible range? 20 hertz to 20,000 hertz. So 800 hertz lies between this range. Thus, we can say this sound can be heard. So in part C, it's a descriptive question. Thus, we need to be careful. We may students mostly lose marks in descriptive questions. Thus, you particularly should practice descriptive questions as much as you can. Okay, now let's look at question C. Describe the motion of the cone in figure 6.1 and explain how this causes the production of sound. Okay. So we know that sound is a longitudinal wave, and how are longitudinal waves formed? By back and forth vibration, thus, which means the cone vibrates back and forward, causing regions of rarefactions and compressions, which are the key principles of longitudinal wave. There is a longitudinal wave, which means there are regions of rarefactions and compressions, or regions of high pressure and low pressure. So let's write the answer. There are 3 marks, thus we need to write 3 points. So first, let's write the cone moves or vibrates. You may write moves or vibrates, both are accepted. Backwards and forwards. We got the first mark. Then for the second mark, we write causing regions. Region. Let's write region instead of regions, because for the third mark we need to write. You'll understand after I write the third mark. After I write the answer for the third mark, you'll understand why I wrote region instead of regions. So causing region of rarefactions and compressions. So we got the 2 marks. And for the final mark, we need to write what. Let's look at the question again. Describe the motion of the cone and explain how this causes the production of the sound. So we described the motion of the cone, that is move backwards and forwards, and the and now we, for the first mark we wrote how the cone moves, and for the second next 2 marks we're gonna write how sound is produced. So I wrote causing region of rarefactions and compression, that is first for the second mark, and for the third mark we need to write vibrations is passed to the neighboring particles. That is, let me first write the answer, then I will explain what I wrote. So it means the cone is vibrating backwards and forwards, causing a region of compression and rarefaction at this state, at the very beginning of the cone. But afterwards, this vibration is passed to the neighboring particles, that is here, which is causing the sound to spread or to move, to progress. The sound is traveling from left to right. So this transferring of vibrations from to the neighboring particles causes sound to progress or move forwards. Thus, I wrote region instead of regions, because the rarefactions and initially the rarefactions and compressions are only getting produced in front of the cone. Later on, the vibrations are passed. Sorry, it's there is a grammatical mistake. It's are instead of is, because I wrote vibrations plural as are passed to the neighboring particles. Let's look at the mark scheme. Okay, for the first mark, it says the loudspeaker cone is vibrating, moving. We wrote moving, thus this mark is applicable because vibrating and vibration and moving means are similar words. For mark 2, when the cone moves forwards, it produces compression, or when it moves backwards, it produces rarefaction. So we did write regions of rarefaction and compression. We don't need to write, as the backwards and the forwards are in brackets, thus we don't need to write when we get a rarefaction or compression, because the reasons are in brackets. Thus this is not mandatory. We just wrote compressions and rarefaction, thus we got this mark as well. Then for the final mark, vibration, compressions, rarefactions, energy, change in pressure, motion passed to the neighboring air or particle or air. As the neighboring air is on brackets, we can write anything instead of air. Or thus we got this mark as we wrote vibration passed to the neighboring particles. Thus we got all 3 marks. Now let's look at question D. The sun is a very large and extremely violent ball of gas. Electromagnetic radiation from the explosions of the surface of the sun reaches the earth. Explain why sound from explosions on the surface of the sun does not reach the earth. So we know that there is a vacuum between the sun and the earth. There is no air between the sun and the earth. And sound is a longitudinal wave. And longitudinal wave cannot travel in vacuum. Longitudinal wave travels on the principle of changes in pressure, which means there are regions of high pressure and low pressure. If there is no air or any medium, there won't be any regions of low pressure or high pressure. Thus, longitudinal wave can never travel in a vacuum. Thus, we can write, it's an easy question, we can write there is no air, is no air or medium. Now let's not write medium. There is no air between earth and sun, and sun. And for the next one, we write sound waves cannot travel in vacuum. I think I made a spelling mistake in writing vacuum. Now, spelling mistakes are ignored, thus there is no worries if you make a spelling mistake in your exam. Now let's look at the mark scheme. Okay, so space is a vacuum. Space means the space between Earth and Sun. There is it's vacuum or no air, medium slash air. So we wrote no air. So we got the first mark. And sound cannot travel in space. Vacuum. Yes, we wrote sound cannot travel in vacuum. Thus we got this mark as well. B C. There is a double C. So we got full marks in question 6. Now let's move on to question 7. So question 7 says that an electric circuit contains a battery, a fixed resistor R, a voltmeter, and a thermistor. So this is a fixed resistor, this is the voltmeter, this is the battery. Figure 7.1 is incomplete circuit diagram of the arrangement. Okay. So the thermistor is connected between terminals T1 and T2. Let's draw a thermistor. Complete figure 7.1 by drawing a circuit symbol for thermistor connected between T1 and T2. Let's draw a thermistor. Thermistor is similar to a resistor, but we just have an extra line between them. That is like this is how a thermistor looks. Yes, the mark scheme shows we need to draw this. If we drew this, we got the mark in part A. Now in part B, the resistance of R is 2.5 ohms. Let's mark it on the diagram. 2.5 ohms. The reading on the voltmeter is 0.4 V volts, 0.40 volts. Calculate the current in R. So we can see that the voltmeter is connected in parallel with resistor R only. Thus, this voltmeter measures the voltage across R. So the voltage across R is 0.4 volts. So we can easily use Ohm's law to calculate the current, that is I is equals to V divided by R. So V is 0.40 divided by what is R? 2.5. Now let's put these values in the calculator. 4 divided by 2.5 is 0.16. Our raw values, which is the values of V and R, were of two significant figures. Thus, the answer we write should also be of two significant figures. Now, in part 2, the power transferred in R. Okay, it's a very easy question. We know the formula of power is P is equals to V times I, when voltage times current. I is current, the symbol of current, and V is the symbol of voltage. Thus, let's do it. We know the voltage is 0.4 times 0.16. Should be very easy. 0.16. The answer becomes 0.064 watts. Let's check our answers in the mark scheme. Yes, the power is 0.064 watts and the current is 0.6 amperes. We got both the 4 on 4 marks in 1 and 2 of part B. Now, part C is an explanatory question. Let's look at it. The temperature of the thermistor increases. Explain what happens to the reading on the voltmeter. So, we can say that, sorry. The temperature of the thermistor increases, which means its resistance decreases. Always remember the resistance of a thermistor is inversely proportional to temperature. For a thermistor only, not for any other conductor. It's the opposite of any other conductor. Any other conductor would have a relationship of resistance increases with temperature, which is resistance is directly proportional to temperature, but for a thermistor, it's the opposite. Resistance is inversely proportional to temperature. Thus, as the temperature increases, resistance must decrease. So, we can say if the resistance of thermistor decreases, so we can say less voltage shared across this thermistor and more voltage will be shared across R. The resistance of thermistor decreases, thus voltage should also decrease. The voltage shared across the thermistor should also decrease. As the EMF is constant, thus as the voltage shared across the thermistor decreases, the voltage shared across R would increase. Thus, voltmeter reading should increase. Now let's write this in the answer. Resistance of thermistor decreases, causing less voltage shared You can also write less potential difference instead of less voltage shared. Both mean the same. Here across thermistor. Thus, more voltage shared across R. More voltage are causing voltmeter reading to increase, causing increase in voltage. Now let's match our answer with the mark scheme. Mark scheme says resistance decreases. Yes, resistance of the thermistor. Yes, we wrote the resistance of the thermistor decreases. We got this mark. For the second part, increase in current. We didn't write that, but we wrote whatever is on the right side of the slash. R takes larger proportion of the total resistance or voltage. Yes, we wrote R takes larger proportion of voltage. We wrote this part and voltmeter reading increases. Thus, we got 2 on 2 on this part. And 7 on 7 for question 7. Now let's move on to question 8. So question 8 says that figure 8.1 shows a permanent magnet attached to one end of an unstretched spring and held at rest just above a solenoid. Okay, this is the magnet. This is an unstretched spring, which means the magnet is being held. When we release the magnet, the spring will be stretched and magnet will fall down into the solenoid. Okay, let's continue. The solenoid is connected to a sensitive ammeter which measures the current. A. State the name of the substance from which permanent magnets are made. So we know by a fact that permanent magnets are made out of steel. That is an alloy of iron and carbon. So let's move on to part B. The magnet is released and moves downwards towards the solenoid. The ammeter shows that there is a current in the solenoid when magnet moves. Explain why there is a current in the solenoid. Very easy. We know that when the magnet has magnetic field like this, magnetic field lines or magnetic field, these are magnetic field lines. So when this magnetic field lines cut a metal wire or conductor, an EMF is induced. That EMF causes the current in the conductor. Thus, when the magnet is released, the magnetic field lines moves the magnetic field lines cuts with the solenoid constantly, like it is moving downwards. Thus, the magnetic field lines is cutting the solenoids at every time while moving downwards, causing an EMF in the solenoid. That EMF is producing the current according to Fleming's rule. Let's write down the answer in a brief way. There are 3 marks, thus we need to write 3 points. Explain there is a current, why there is a current. Okay, so we say magnetic field lines cut the solenoid causing a change in magnetic flux. So you can choose not to write causing a change in magnetic flux. This is optional, but I wrote to be safe because none of you and I knows what's in the mark scheme. So to be safe, I wrote causing a change in magnetic flux. Okay. So this induces. We always need to write this induces an EMF. We can never write this induces a current. We first need to mention EMF, then from that EMF we would mention a current. This induces, INDUCES, induces an EMF on the solenoid. Now that EMF induces or produces. Let's write produces instead of, as we wrote induces once, let's not write it twice. Induces, or oh, sorry, that EMF produces current. Current in the solenoid or on the solenoid, same thing. Let's look at the mark scheme. The mass scheme of 8B1 says magnetic field lines cut the solenoid. Yes, we wrote this. We got the by saying changing magnetic flux, we mean magnetic field changes. That's the same thing. Flux and field basically means the same thing. Thus we got the first mark. The second mark, EMF induced. We got this mark. Electromotive causes current. We got this mark as well. We got 3 on 3 in this question. Okay, now let's move on to part 2. Part 2 says the current causes the top end of the solenoid to become a south pole of an electromagnet. The bottom end of the permanent magnet is an south pole. Explain why the top end of the solenoid becomes an S pole, that is south pole, as the magnet moves downwards towards the solenoid. So the question says, as the magnet is moving downward, the top end of the solenoid, this is the top end, becomes an S pole, and the bottom end becomes a north pole. S pole means south pole, N pole means north pole. So we know, according to Lenz's law, whenever there is a change in magnetic flux, there is a force induced opposing the change, which means if the magnet is moving downwards, a force would be produced, according to Lenz's law, pushing the magnet upwards, because the purpose of the force is to oppose the change in magnetic flux. The change in magnetic flux was causing due to the magnet moving downwards, thus a force would be induced on the magnet upwards in the opposite direction. Thus we know that like poles as a repel, thus as the top is an S pole and also the bottom of the magnet is an S pole, thus these two parts will repel each other, causing the magnet to slow down, opposing the change in magnetic flux. Now we need to write this answer in a brief way. There are only 2 marks. Let's write. According to Lenz's law, there is not much space, thus we need to write with small letters. L-E-N-Z-S, Lenz's law. A force is there to oppose the motion. Oppose the motion. Is produced. Let's write produced. A force is produced there to oppose the motion. Thus, both S poles repel each other. Repel. I wrote the wrong spelling. Each other, opposing the motion. So what I wrote is, according to Lenz's law, a force is there to oppose the motion of the magnet. Thus, both S poles, as the top of the electromagnet and the bottom of the magnet are S poles, electromagnet is the solenoid, are S poles, thus both S poles repel each other to opposing the motion. Now let's look at the mark scheme. The mark scheme says Lenz's law mentioned or oppose the change. We mentioned Lenz's law, so we got this mark. Repel magnets. Okay, we wrote this, that to both S pole repels the magnet, or upward force. We didn't mention upward force, but we did mention a force. Thus, we won't be getting this mark, but as we have written repels the magnet, we will be getting the entire mark, because it's an or, it's not mandatory to write upward force. We can write any of these 1, 2, 3, 4, 5 answers. Let's look at the other one, repulsion. We wrote repulsion. To oppose the magnet, we did write opposing the motion. Resist motion of the magnet. We also wrote this one. So we got 2 marks in this question. Now let's move on to part C. The magnet oscillates up and down. Describe what happens to the current in the solenoid. So As the magnet is connected with a spring, first after the spring is released, the magnet will go down, then it will come, go, get back, then again go down, then again get back. As we know, whenever we drop something with a spring attached to it with at a fixed point, the thing oscillates up and down in real life. Thus, the magnet will also oscillate up and down. So, what if the magnet oscillates up and down? When the magnet is moving downwards, there is a current induced in the solenoid in a particular direction. Let's say the current is in this direction when the magnet is moving downwards. But afterwards, as the magnet is oscillating, it will move upwards. Then the direction of the current would change in the opposite direction because field lines are cutting in the opposite direction. Initially, the magnet was traveling downwards, now it's traveling upwards. Thus, in both cases, the direction of the current could change. One more thing, that is when the magnet, as the magnet is oscillating, which means it is accelerating plus decelerating. Like when the magnet is at its lowest point, it has zero velocity of zero speed, and after at its midpoint it has maximum speed, which means it once accelerated and once it decelerated to zero speed and it once accelerated to its maximum speed, which means the magnitude of the current would also increase and decrease because the faster the magnet moves, the greater the current we get. So as the speed of the magnet increases and decreases continuously as it oscillates, we can say the magnitude of the current also increases and decreases and the direction changes. These are the 2 points I think we need to write to get this 2 marks. So let's first write the current direction. Current direction, DIRECTION, changes and the magnitude of the current in of not of in not in of the current increases and decreases as speed of the magnet moving increases and decreases. So this part, as speed of the magnet moving increases and decreases, is not necessary to write, but I wrote to be safe. You can only write till this much. You don't need to write as they didn't ask for the explanation. They just asked description. Because we don't need to write the explanation. Let's look at the mark scheme. The mark scheme says current changes direction. We got this mark. We wrote this, and the magnitude size of the current changes or increases slash decreases. So we wrote both. Thus, we would be getting this mark. Magnitude of the current changes. We got this mark and this mark as well. Thus, we got a 2 on 2 on this question and an 8 on 8 on the entire question. Now let's move on to question number 9. I think this is the last question. Yes, question 9 is the last question. Now sorry, there is a question 10. Now let's look at question 9. So question 9 says that question 9 says that in space an interstellar cloud of dust and gas collapses to form a protostar. Protostar is the second stage of a star's life cycle. The first cycle, in the first stage, we have an interstellar cloud of dust and gas. The cloud contains hydrogen. Describe the energy transfers that take place as the cloud collapses and forms the protostar. So we know the cloud collapses only due to gravity. The gravitational pull towards the dust and gas causes the gas particles to come close and collapse, form a protostar. So we know due to as gravitational pull is causing the collapse, so we can say gravitational energy, potential energy, that is GPE. Let's not write GP, let's write the full form, gravitational potential energy is converted to So we know when a protostar is formed, there is a high pressure or there are high speed hydrogen atoms, hydrogen nucleuses at the core that is causing hydrogen fusion, hydrogen fusion or nuclear fusion. So we say that gravitational potential energy is converted to kinetic energy. Energy. Also, there is high temperature at the core. Thus, we can say and kinetic energy and internal energy. That is another form of heat energy. But it's not fully heat energy, but it's somewhat similar. It's not fully heat energy, but we mostly use internal energy when there is an increase in temperature. Not necessarily that when is the increase in temperature, there has to be a change in heat energy. If there is an increase in mass, then there is no change in heat energy. But if there is an increase in temperature, there has to be an increase in internal energy. So gravitational potential energy is converted to I forgot to add a to kinetic energy and internal energy. So I think this should be enough. Let's look at the mark scheme. Uh, any two from in 9A from gravitational potential energy or gravitational potential energy to kinetic energy mentioned. Yes, we did mention this part and we did mention from as well. No, we didn't mention from, but we did mention the two gravitational potential energy to kinetic energy mentioned. So we mentioned this part. Also, we mentioned the internal energy as well. So we got the 2 marks in 9A. Let's move on to 9B. The collapse results in nuclear reaction in the protostar that involves the isotope hydrogen 3. This is the symbol of hydrogen 3 nucleus. The isotope of hydrogen 3 is radioactive. This decays by beta particle emission. State how the nuclei of isotopes of the same element are different. Yes. The only difference between isotopes are that the nucleuses have different number of neutrons. So we can write the nuclei has different number neutrons. This is the only answer to this question. Okay, now let's move on to part 2. Explain why hydrogen 3 cannot decay by an alpha particle emission. So we know an alpha particle got 2 neutrons and 2 protons and a total mass of 4. So now we know that hydrogen 3 nucleus has only 1 proton, but alpha particle requires 2 protons. Thus, the hydrogen 3 nucleus cannot undergo alpha particle emission due to lack of protons. So let's write 3H1 has 1 proton, but alpha particles require. Let's erase this part of particles have 2 protons. Thus, hydrogen nucleus cannot undergo alpha emission. Let's look at the mass scheme. Only has 1 proton. Yes, we got this mark. As we wrote, it has 1 protons or not enough protons. We got this mark. Okay, so let's move on to part 3. Complete the equation for the decay of hydrogen 3 to an isotope of helium H. Let's see. So we know the equation of beta emission. During a beta emission, with the beta particle had a proton number of -1 and mass 0. Whenever there is a beta emission, proton number increases of the final product. So if the initial nucleus had 1 neutron, had 1 proton, the final nucleus would have 2 protons, and the mass number remains the same. We add whatever on top. Like here on the left hand side of the arrow, there is 3 mass number on the top. Also on the right hand side of the arrow, there is 0 plus 3, which is 3 mass. Now let's balance the proton number. Hydrogen has 1 and beta particle -1, helium 2. If we add both, 2 minus 1 becomes 1. So this is the equation. Now let's move on to part 4. Explain how the nuclear reaction in the protostar stops further collapse as the protostar becomes a stable star. Okay, this is very easy. We know that the gravity is pulling, let's say this is the star, the gravity is pulling stars inwards, but due to high temperature and pressure, there is an outward radiation force. There is a force due to radiation. The high temperature and pressure causing fusion in the core is producing an radiation, emitting radiation that is pushing stuffs outwards. The gravity is pulling inwards, and the radiation pressure is pushing outwards. This cancels out the force and causes a balance. Let's write this. Let's write this thing as the answer. Okay, let's write. We need to write three information. First, let's write due to high temperature. Explain as we need to. Due to high temperature, there is an outward force that cancels out the inverse gravitational force. Sorry, gravitation. I think I made a spelling mistake. Here there won't be any I. Gravitational force causing a balance. Right. Of zero. Imbalance. This should be enough. Let's look at the mark scheme. High temperature in the core. Yes, we wrote this part, high temperature. Outward force. Yes, we did write outward force due to the high temperature in the nuclear reaction. We did write this part. And balances gravitational force. We also wrote this. Thus, we got the 3 marks in 9V4. Let's move on to part C. The cloud of dust and gas that collapses also contains atoms of the heaviest elements. State which part of the cycle of a star is responsible for the production of the heaviest elements. Okay, so here it says when there was an interstellar cloud, there were heavier elements present. So, how were those heavier elements produced? Like, if this is the cloud, if this is an interstellar cloud from which Apollo star would be born shortly after. So there were heavier elements like iron, Fe, Fe. Fe is a symbol of iron. There were a few heavier elements present. So where did these heavier elements come from? So we know that at the end of a star's life cycle, they start to fuse hydrogen into heavier elements. First, hydrogen is fused to helium, then helium is fused to other elements from other heavier elements. Like this way, slowly, heavier elements are produced at the core of the sun at the end of its life cycle. Then, when there is a supernova explosion, all the heavier elements at the core are are exploded and spread out into the space, and that heavy elements afterwards join together in an interstellar cloud with other hydrogen atoms or other elements. So the source of these heavier elements are from a supernova explosion. Whenever there is a supernova explosion, that is the death of a star, heavy elements from its core are spread out into the universe space, and few go join into other interstellar clouds that contain hydrogens or other elements to form a new star. So the answer would be a supernova explosion. Explosion. That's an O. Pardon my handwriting. So when there is a supernova explosion, all the heavier elements from the core of a dying star are exploded and spread into the space, which then further joins, goes into an interstellar cloud where there are other elements along with the heavier elements. Thus, this is the answer. Let's look at the mark scheme. Yes, the mark scheme says supernova explosion. So we got this mark. Let's move on to the final question of part. So question 10 says that the isotope iodine 131, that is the mass number of iodine, emits two types of nuclear radiation. Gamma radiation is one of the types emitted. A sample of iodine 131 produces a narrow beam of radiation which passes into a magnetic field. Figure 10.1 shows some of the paths taken in the magnetic field by the radiation emitted from the sample. Magnetic field directed into the page, which means the magnetic field is traveling from out of the page and going into the page. It's in this direction. If you look it from this view, like if you looked it from this side, the field would look like this, going this way, which is into the page. Okay, now let's continue. The direction of the magnetic field is into the page. It's written here. A1, figure 10.1, marked with the symbol gamma, it's the gamma symbol, any of the paths taken by the gamma radiation. So we know that gamma radiation is a photon. It does not have any mass. Thus, it does not have any charge. Thus, it won't get affected in a magnetic field. It will just go straight through a magnetic field as it is a photon. It does not have any mass. It does not have any charge. Thus, this ray is the gamma radiation, as its path is not affected by the magnetic field. Now let's move on to part 2 to determine the other type of radiation emitted by the iodine. Okay. So now if I use the Fleming's left hand rule, that is, we direct our pointer finger towards the page. The pointer finger is the direction of the it is the direction of the magnetic field. That is, if my pointer finger, if let's consider this dot as the pointer finger, as this is going into the page. This is my second finger. That is, no, we don't actually use the force. Sorry, the force on the particles are downwards. We can see that the particles or radiation were coming this way, then it went downwards. So the force is downwards. So my thumb is pointing downwards. This is the thumb. This is the pointer finger that is going into the page. Thus, my second finger would go this way. It's like, I cannot draw my hands properly because I'm unable to show you what I mean. My pointer finger is going into the page. My thumb is pointing downwards. That is the direction of the force. And my second finger is pointing to the left, which means the current direction is to the left. So we know whenever a negative charge moves, the current direction is opposite of that of the negative charge. So if the current direction is backwards, the negative charge should move in the opposite direction. So now we can say these are beta particles, as the direction of the radiation is opposite of the current direction. Is in the opposite direction of the current direction. Thus, it is a beta radiation. Beta radiation. Now I explain why. Now we just need to write why do we think it's a beta radiation. Let's write. Let's mention according to the left hand rule. Pointer finger into the page and finger into the page causing us not causing and the thumb, because we can control where the two of the three fingers would point and the other is determined by the position of the two fingers. Thus we controlled the pointer finger into the page and the thumb pointing below. Below, causing the other finger the left. Thus, current, current direction is current moving towards the left. That's right, current moving towards the left. So we wrote according to the left hand rule, we mentioned the left hand rule, the pointer finger is pointing into the page, my thumb is pointing below, this is the thumb, TM thumb, and this is the other finger, that is the direction of the current. So the current direction is towards the left. So as the current direction is towards the left and the radiation direction is in the opposite direction, thus it has to be a beta particle. Let's look at the mark scheme. The mark scheme says this is a beta radiation. Yes, we got this mark. Left hand rule mentioned, we did mention left hand rule. First finger into the page, that's the pointer finger, and thumb downwards. We got this mark as well. Below and downward, same thing. Current opposite to the motion. I think we didn't mention opposite to the motion. We mentioned current moving towards the left. We had to mention opposite to the direction of radiation. Current opposite to the direction of radiation. We missed one point. Thus, we missed one mark. We got a 2. So, we have to be careful while writing these answers, but thus, because we might miss out a point and we might miss the mark. So, we have to write the current in the opposite direction of the radiation or the motion. That would mean it's a beta particle. Now, let's move on to part 3. In another experiment, the beam of radiation from the sample is incident on a 5 millimeter thick sheet of lead, which is enough to stop beta particle but not gamma particle. Gamma radiation, not a particle. Gamma is not a particle, it's a photon, that's a radiation. State what happens to the two types of radiation in the beam. So let's write beta radiation gets completely absorbed. It gets completely absorbed and gamma radiation passes through. Though some of the gamma radiation would get absorbed, but most of the gamma radiation would pass through because thick lead, 5 millimeter thick sheet of lead is not enough to stop gamma radiation. Passes through. Beta, and it is enough to stop beta particles but not gamma. So I think this should be enough. Yes, beta radiation completely absorbed. Some gamma rays absorbed or gamma rays passed through. So we wrote this part then. So we got this. Now you may ask, there is a underline below the sum in the first part. So we should mention sum, not necessary, because if we wrote this much, some gamma radiation rays absorbed, then we must add some because not all gamma rays are getting absorbed. A few gamma rays are getting absorbed. So we had to write some when we wrote, if we have written this much. Now that we have ignored this and wrote only this much, we don't need to write the sum because there is a bracket. Gamma rays pass through. We wrote gamma rays pass through, which means we got this one as well as this one. A 2 on 2 in 10A3. Now let's move on to the final part. The gamma radiation produced has a frequency of 8.8 into 10 to the power 19 hertz. The speed of the electromagnetic radiation in a vacuum is 3 into 10 to the power 8 meters per second. Calculate the wavelength of this gamma radiation in a vacuum. A very simple math. We need to use the formula of the speed of a wave, that is V is equals to lambda. This lambda means wavelength, frequency is f, v is speed. So if we need to make lambda subject, plus we take it to the other side, that is v by f. If v is 3 into 10 to the power 8, sorry, we got 8 and we divide it with frequency, that is 8.8 into 10 to the power 19. Then let's put the values into the calculator. 19. We get 3.4 into 10 to the power minus 12 meter. It's not 30. The raw values were given to two significant figures, thus our answer should also be of two significant figures. 3.4 into 10 to the power minus 12. This is the answer. Let's look at the mark scheme. Yes, the mark scheme says 3.4 into 10 to the power minus 12 meter. So we got it right as well. So this is it. We have solved the entire paper. If you have any confusions with any part of this paper, you might want to watch the solution of that part again. You might rewatch that part of the video. So till then, stay tuned with Chester Academy. Assalamu alaikum. Bye bye. Have a good day.